right, so we are starting on Unit 9 as the last unit before the end of the semester. And for this unit, we are going to be looking at kinetics. First off, to start with kinetics, we will be looking at just the rates. And for those of you who have been taking physics before, do remember that what it means is when you're doing a rate, you are actually looking at basically a speed. It's a velocity. In our case, our velocity is for the concentration and how the concentration is changing compared to the amount of time. So rather than in physics where you might be doing a distance versus time, this time we're doing a velocity versus time. What you will notice as well is that when the rate is negative, we are referring in fact to a reactant. And we're referring to a reactant because if you might remember from velocity, it is actually based off of the graph. So you're doing a change in y versus a change in x. And in our case, we're going to plot along the y our concentrations, and we're going to plot along the x our times. So having done that, reactants will be decreasing. They should be going down in concentration as the time progresses because we're measuring the remainder of the reactants. Same sort of thing with the products. It should be going up in concentration because, again, we're measuring the remainder of the product, or really what's being produced. So we have down here just an example of a graph. And as you look at this graph, we're going to zoom in just a little bit more, which might be a little too much, but that's all right. This particular graph happens to be showing us a nitrogen reaction with nitrogen pentaoxide reacting to form nitrogen dioxide as well as oxygen gas. What you can see, if you look very closely, is that this curve here goes along the nitrogen dioxide. Again, notice that that happens to be a product, and so we can see that our curve is in fact increasing. We also have this bluish curve is going down. That is our reactant, and that's our dinitrogen pentaoxide decreasing as it is reacting. And then finally we have oxygen, and oxygen is also increasing because it's another product. Some things to notice. There are these little boxes here, these little triangles that are sort of colored in, and those are representing our initial rates, also known as our instantaneous rates. They're instantaneous because they're just looking at a particular area of the curve. So in one instance, it's time of 300 to 400 seconds. And in another instance, as we look over to the right, we're going between 600 and 700 seconds. You can see in each of the curves that the curve starts out as a rather steep slope, whether it's going as a positive slope or it's going as a negative slope. And as the time progresses, you can also tell that that slope starts to reduce. So it's not nearly as steep. These instantaneous rates then show you that the speed is fast at the beginning, and then as we progress over the amount of time, it begins to slow down. Okay, and you can see that we're doing basically a tangent idea here, solving for that slope. In addition, you can see that the amount that we started with respect to our dinitrogen pentaoxide, as we go over here, this amount of difference is the full change of the dinitrogen pentaoxide. And notice if we compare that to how much it changed for oxygen, right? Oxygen started down here at the bottom. Whoops. And since it started down here at the bottom, if we take a look to see how much oxygen changed by, you can tell that the amount that oxygen changed by, this distance, is approximately half the distance of the dinitrogen pentaoxide having changed. So if you measure this length, you'll see that it's actually 2 of those lengths for the amount that the dinitrogen pentaoxide changed. Now, if you're looking at your balanced equation, you may already notice that that means that we are changing our coefficients. The coefficients impact how much your reaction is going to be altered by. So you can see that these are then going to be related to each other with respect to their coefficients. You can also tell that that means that the amount that was changed with respect to the nitrogen dioxide should be approximately 4 quantities of oxygen, which you can see is roughly from here to the oxygen, about midway, up, and then 1 more. So it is in fact 4 a distance change, or really a concentration change. Okay? If we wanted to take the equation, right, and solve for those slopes, you really could. And we could make a relationship between them. So if we wanted to know the rate of disappearance, and we wanted to make it for the dinitrogen pentaoxide, and make it equivalent to the rate of appearance of our NO2, we could set our 2 rates equal. So the disappearance would be the N2O5, versus the change in time. And the appearance would be the NO2 versus the change in time. In order to actually make these equal to each other, remember that the N2O5 is a negative slope because we're losing it. So to make it equivalent, we would put a negative sign in front. In addition, the N2O5 is decreasing 2 times to the 4 times the NO2 is increasing. So in order to do that, I usually think of it as just putting that coefficient into the denominator. So there'll be some questions in which you want to have a ratio or a comparison of a product to a reactant. And remember that they will always be able to be compared as long as you have your balanced equation. Okay, so let's go ahead and turn the page. And as we take a look at our next couple of examples, right, we have peroxydisulfate ions that are oxidizing the iodide ions. And again, you're being asked how the rate of the reaction that is expressed as the rate of formation of I3- relates to the rate of reaction of I-. So we're looking for the rate, so that would be change in I- compared to the change in time. And then you want to compare it with the change in I3- and the change in time. So again, since the I- is in fact a reactant, it's got a negative sign in front of it, while the I3- is a product. So its slope would be positive, the I-'s slope would be negative. And then again, in order to make them equivalent, it's a 3-to-1 ratio. So for every 3 iodides that are reacting, we'll create 1 I3-. All right. Calculate the average rate of formation of O2 in the following reaction. And so now we're looking at an interval of time. And so again, in order to solve for the O2, you might be given something like this, where you want to check the difference. So our rate would be the change in oxygen, so 0.0048 minus 0.0036. And then in the denominator, 1800 minus 1200. So that'll give us a change in concentration of the oxygen. Notice that our oxygen again is a product, so we should end up with a positive value here. So now we have 0.0012 in the numerator and 600 in the denominator. So we should have right around, I guess, 2 times 10 to the negative 6th. And then again, our unit would be molarity, and then in this case, our time was in seconds, so molarity per second would be our rate. And if for some reason, right, again, that's our rate of oxygen, if for some reason you were then asked for maybe the rate of NO2 instead, again, you can set your NO2 rate as an equivalent value to your oxygen. Both are products, so they would both be positive, but the NO2 would have a 4 times the change in time. So if I wanted this rate, notice I would take the oxygen's rate and substitute in 2 times 10 to the negative 6th. And again, that would be meters per second. And then because I would want the change in NO2 over the change in time, again, we would multiply that by 4. So we would end up with 8 times 10 to the negative 6th meters per second as our NO2 rate. So you want to get comfortable with 2 versions, right? The first version is that it's change in concentration over change in time. And the second version is that you're actually calling that by the name rate. And that's going to be super helpful in this next section.